Design and Analysis of Algorithms class. Myself, I am Shravani, Assistant Professor from the Department of CSE. In today, I am going to start one of the application of backtracking, which is n-queens problem. Now, in today's lecture, I am going to cover what is meant by n-queens problem, and also we will see the solutions of 4-queen and 8-queen problem, and also we will see the algorithm for 8-queen problem, and we'll see the examples of it. Right? And the main objective of today's lecture is the students are able to understand the concept of n-queens problem and outcome. After learning this lecture, the students are able to apply this n-queens problem on the given problem instance. Now, what is meant by n-queens problem? Right? So here given an n by n chessboard, given an n by n chessboard, and there are n queens are given to you. N queens are given to you, and you are supposed to keep all these n queens in the given chessboard such that here no queen should attack each other. That is either row wise or column wise or diagonally. In any manner it should not attack. No two queens should attack each other. In such a manner I have to keep all these queens within the n by n chessboard. Right? That is the n by n problem statement. Now let's see what is a 8 queens problem about. So when n is equal to 8, this is 8 queen problem. Right? So now 8 queens problem, here there are 8 queens, and which where I'll be given with 8 by 8 chessboard. I'll be given with 8 by 8 chessboard, and here I'm supposed to keep the 8 queens within this chessboard, right? And such that no two queens should attack each other, either row wise or column wise or diagonal wise. And here in this figure I'm showing you one of the solution of 8 queens problem. Here in the 4th column I have placed the q1, and in the 6th column I have placed the q2, right? So here the solution we can represent in terms of tuple as 4, 6, 8, 2, 7, 3, 5. Right? 7, 1, 3, 5. So 4, 6, 8, 2, 7, 1, 3, 5 is the tuple solution for 8 queens problem. And not only this, here there can be number of solutions. Even how many number of solutions we can make for a given problem instance also we can see in the next, okay, in the next slide. So now this is about your 8 queens problem statement. Now here I am showing the solution state space tree for the 4 queen problem. So now let's let us know how to solve the 4 queen problem. Let us know the solution about 4 queen problem. So initially you will be given with an empty 4 by 4 chessboard, and you will be given with 4 queens, right? So for suppose I have kept, okay, this is my root node where I'm having empty chessboard, right? Now I want to keep q1. So the q1 can be placed in the 1st column or 2nd column or 3rd column or 4th column, right? So even I can place it in the 4th column. Here I am placing in the 4th column, right? So these are the 4 possibilities initially. Now coming to the next level, right? So here q1 is placed over here. So now q2, can I place q2 over here? No, because here column wise it is attacking. Now can I place q2 over here? No, here diagonally it is attacking. So I can place q2 only in this position and in this position. So I will be having only 2 options, right? The first option is here q1, and here I can place it, right? So which is q2, and q1 and q2 I can place it over here, right? Now for the next iteration, here can I place q3 here? No, because row wise attacking. here no, here q2 is attacking, here no, here also no. So for this I cannot expand, so simply backtrack, simply change the path. Now coming to here, here also q2 I can q3 can I place here? No. Here yes, here I can place this, right, in the next level. Whereas here no, I cannot place over here, even here also I cannot place, right? So q3. Now again coming to q4, here no, here no, here no, because diagonally attacking, here also no, so here also backtrack, change the path. So now in this particular one, now I have changed this path to this, which is here, as I could not find the solution, now I am changing my q1 to this place. Now again q2 can I place here? No. Here no, here no, here yes, I can place it there. So now q1 and here is my q2. Now coming to q3, shall I place it here? Yes. Now coming to q4, here no, here no, here yes. So this is one of the solution for 4 queen problem, right? So likewise in this figure I have shown you the 2 solutions for 4 queens problems, and this is about state space tree. Here the state space tree for 4 queen problem I have shown you. So here I have explained you that, right? Now this is the algorithm for placing 8 queens in the 8x8 chessboard for the 8 queen problem. And for 8 queen problem, here I'll be having 2 algorithms. One is place algorithm and the other one is n queens algorithm. Place algorithm is used for checking whether a particular queen can be placed or not in the corresponding column, whereas n queens algorithm is going to give you the tuple solution. For suppose for this particular 4 queen problem, here the solution can be, in second row I have kept q1 in the 4th column, and here in the 1st column, and here in the 3rd column. So 2 4 1 3 will be the tuple solution, right? So this solution I can get it from n queens algorithm, whereas place algorithm is used for knowing whether I can place a particular queen in that position or not. Now let's see about the first algorithm, which is place algorithm. So here it will returns true if a queen can be placed in the kth row and ith column. Now here for suppose I'm having I comma j as one position and k comma l as one position of q. So if suppose I'm having I minus k is equal to j minus l, in that case here 2 queens are attacking diagonally. Please remember, if I minus k is equal to j minus l, in that case the 2 queens are attacking diagonally. So I need to remove such pairs, I need to take another path, right? So for that, here initially the place of k, so here it returns true if a queen can be placed in the ith row and jth column, and here it will returns false whenever I cannot keep a corresponding queen in that particular position. Now for j is equal to 1 to k minus 1, what I am checking here, if a of j is equal to I, or absolute of a of j minus I and k minus l, nothing but here this in turn I can written as I minus j and k minus l, right, which implies I can written as I minus j is equal to k minus l. If this case, nothing but here if I am applying absolute on both sides, right? So that will be the next case. If a of j is equal to I, and even this case, so if this case is evaluates to true, which means that row wise attack, and if this case is evaluates to true, Now in that condition I can say that the queens are attacking diagonally. So when these two cases are evaluates to true, any one of the cases evaluates to true, I simply return false because there is a row attack and a diagonal attack. Now in turn we have implicitly checked even for the colon attack, right? So otherwise I should return true. If both the if any one of the condition is evaluates to true, I have to simply return false. Otherwise I have to return true. That is about your place algorithm. Now corresponding to n queens algorithm is used for finding the solution, that is a tuple solution, right? So here for that, for I is equal to 1 to n, here if place of k comma I, what it mean if place of k comma I, if this is resulting into true, which means that I can place that corresponding queen. So simply I can add this queen to the solution. So that's why here I am writing x of k is equal to I. If place of k comma I is evaluates to true, then simply I am writing x of k is equal to I, the corresponding colon value. Now if j is equal to n, then what happens? J is equal to n means I have reached the last row. So when I am reaching the last row, what I have to do? I have to simply write the entire tuple solution. So if j is equal to n, simply write the entire solution. Otherwise what happens? J is not reaching to the end of your row. So in that case, simply I have to call the n queens problem with k plus 1 comma n. So then it will takes the next row and the corresponding queen. Again it will checks for the queen whether I can place it in that particular position or not, and again it will checks for this condition if a of j is equal to I, whether row wise it is attacking or not, and also it will checks for this condition absolute of I minus j is equal to absolute of k minus l, whether it is attacking diagonally or not. If any one of the condition is evaluates to true, simply it will returns false. Once the place algorithm is returning false, then no queen will be placed in that particular position. Now if place algorithm is returning true, in that case it is going to add for my solution, that is x of k is equal to I. Now after that, when I am reaching to the end or when I am reaching to the last row in my chessboard, which is nothing but if when j is equal to n, in that case simply I'm writing the entire tuple solution like this, right? That is write x of 1 to n, right? Otherwise I need to call the same n queens algorithm with k plus 1 comma n, because there are some rows or some queens left in the n queens problem. Now these are the total number of nodes in the 8 queen state space tree. If I want to draw the entire state space tree for the 8 queen problem, so 69,281 states. 69,000 here in this state space tree, this is one state, this is one state, this is one state. So each and every combination or each and every decision is itself a state. So likewise, if I want to draw the state space tree for 8 queens problem, it will have 69,281 states for this state space tree, and the formula is also given here. Right? Summary. So today we have seen what is meant by n queens problem, 8 queen, and even the 4 queen problem, and we had also seen the state space trees, right? In the next class we are going to cover sum of subsets application. Thank you.